No. So you can look up front on the top of your page. We got kind of just a single thing like yesterday we're going to do. The first few days of this unit is really just about kind of identifying things and being able to, put a name to them and justify why, they are a function. That's what we focused on yesterday. Today we're going to focus on a specific type of function called a linear function. What does the word linear sound like? Line. So this is all about today graphs that make a straight line or functions that make a straight line. And we're going to be able to identify linear functions using graphs, tables, and equations. The class you took last year was called, if you went to Heritage or Friendly, was called linear algebra, which means you really only dealt with things that made a straight line. So we start like we did yesterday, kind of in our box with a few definitions. So a linear function in two variables, because we need an input and an output. So x is our input and y is our output, like we talked about yesterday, is an equation that can be written in the form y equals mx plus b. And that is something you talked about last year. We call that slope-intercept form. That's how you graph a line where m is your slope and b is your y-intercept. X is your input, y is your output. Any linear equation we can kind of write to fit that form. And we'll work with that when we get to the equation piece. And then a linear function is a function that when we graph it, it is a non-vertical straight line. So as long as it's straight and not straight just like up and down, as long as it has a little bit of a tilt to it, we can call that a linear function. So any type of diagonal line, whether it's going up, like going up a hill, or going down a hill, it's linear. A nonlinear function does not have a constant slope or a constant rate of change. So if you think you're going up a hill, just up a diagonal line, you're always going to be walking up kind of at the same pace. If you're walking down a hill, you're walking always at the same pace. That's what we mean by rate of change. You're going up or you're going down by the same amount. You'll see in the first example, we can actually just go to the first example now, example 1a. If you're going, say you're starting up here, let's say you're riding down a sled, you're going to go really fast all the way down this way. Once you get to the bottom, you're going to kind of slow down. And then when you start going back up, it's going to be slow going back up, and then you'll keep going like you would go on a roller coaster. You change speeds. All right. So that's one way we know that this here is not a linear function. What's maybe the easier way to say this right away, that it's not a linear function? Because it's curved. And that's all we have to do for a justification as well. On the bottom, it just wants you to pick yes or no. So we would all pick no, not a linear function. And again, our explanations, we can keep them short. We're just going to explain what we see. We're going to say no because it is not a straight line. That's as easy as it has to be. So looking at the next example, the next graph, you should be able to do that now. Everybody should circle yes, and you could just change your reasoning. Well, this is a straight line, and we're just going to be a little bit more specific. We're going to say yes because it is a non-vertical straight line. Why we say it has to be non-vertical, we'll kind of get into this more as we get into our graphing. A line that goes straight up or down doesn't have any constant rate of change. So we can't say whether it's linear or not. We call the slope of a straight line is undefined. So that's why we have that part in our definition of linear. A non-vertical straight line. All right. We have 1/3 of our learning target done. Now we're going to look at tables. Does a table represent a linear or a nonlinear function? All right. We're going to look for also how we can justify that. When you're looking at a table, you're looking at how the inputs are changing versus how the outputs are changing. So remember, X are the things that you're plugging in. Y's are the thing you're getting out. So when I plug in a 3, I get out a 36. When I plug in a 6, I get out a 30, and so on. And what's my pattern with my X values? How are my X's changing when I'm going through the table? Up by 2, 3, up by 3. So I like to so our X's, we're saying going up 3, up 3, up 3. We say our inputs are going up at a constant rate, increasing by 3 each time. With my Y values, is there a pattern? You can just nod your head or shake your head so I know you're there. Yes. The pattern, we're going down this time, or we're going down by 6 each time. So we're decreasing by 6, decreasing by 6, and decreasing by 6. So again, that's constant as well, going down by the same amount each time. If our X's go up at a constant and our Y's go down at a constant, we know this is linear. And to justify this, we could again just keep it simple. We could say, yes, it is linear. And why is because our inputs and our outputs, and that's the key part, your inputs and your outputs have to have a constant rate of change. There's probably when you get to the delta math part, there's some questions like this that are a little tricky. That kind of may jump from it may leave out part of the pattern. It may go from straight 6 to 12. The easiest way when you get to delta math, and I'm sure some of you will have some questions about it, I'll talk to you about kind of filling in the gaps of your table or in your points so you can see the full pattern, not just pieces of it. Any questions so far? Kyrie, can you take your AirPod out for me? Thanks, bud. All right. We got 2 more, and we're talking about equations now, our last piece of our learning target. Do the following equations represent a linear or a nonlinear function? So if you go back to kind of the first bullet point of our little notes box, a linear function can fit the form y equals mx plus b. And again, this is flexible too. And what I mean by flexible, if it's not written exactly like this, it's still okay. And before I get more into the weeds, remember x is our input, y is our output, and m and b just stand for any number we could plug in. All right. If it's not written like this, we could have it written like if our y is on this side, do these two things mean the same? Did I break any rules here? Are these still equal to each other? Yes, we can flip equal signs. It stays equal. What if I change the top one so it looks like y equals b plus mx. Do these two things, is this still in the same form? Or are they both equal? Did I change anything about these two besides the order? No, because 2 plus 4 is the same thing as 4 plus 2. So it doesn't matter the order that we add. Subtraction's a little different. So don't just be like locked into, oh, it has to look exactly like this. The x has to come first, and then the b has to come after. We can shift things around. So all that to say, when we're looking at equations to determine if they're linear, what I like to do is just write that y equals mx plus b form right below it. And we can see it keeps the same form. The y is in the y spot. The x is in the x spot. This 9 is in the place of the b. The only thing we're missing is something in the place of the m. But I've said this before. Math people are lazy and they like to write as like least amount as possible. So we have that floating 1 there. So the m, that 1 is in the place of the m. So this fits the y equals mx plus b form. And that's all we have to say to justify. We could say, yes, it's linear. So it fits the form y equals mx plus b. And the key thing about linear in that form is that there's only one x. And why I think that strategy of just writing the linear form below it and comparing the two is because when you do it below here, the difference pops out to us. Here we have an x squared. Here we just have an x. An x squared is taking x times x. So we know this can't fit. Here we have 1 x's, here we have 2. This is what we would call a quadratic function, which is something we won't get to until second semester. So for this one to justify, we would say no, or nonlinear. And then I'm going to give a specific reason as to why it's nonlinear. And what's making this nonlinear is this x squared here. So I'm going to say x squared, I'm going to call it out, put them on the spot, say x squared does not fit the form y equals mx plus b.